Okay, so today we are going to learn about a theorem from the first chapter of Sakurai, that eigenvalues of a Hermitian operator A are always real, and the eigencats corresponding to such different eigenvalues are always going to be orthogonal. So as we know from the eigenvalue equation, let's say some operator A operating on a vector giving me the same vector with this. Let's say this is my equation 1. Since A is Hermitian, it means that A dagger same as A complex conjugate transpose, if you would like, and from dual correspondence A x on A, then the reverse, A prime. The dagger operates on the gray part. Let's say this is different vector A double prime. Since A dagger is same as this, it means this will be A, and the corresponding eigenvalue is A double prime. And putting the star here to indicate this is a possibly a complex number. I'm getting the same vector here. Say this is equation 3. Okay, fine. So if I multiply this equation by this reversed, then I will get A double prime, A prime. So if A acts on this, I will get A double prime, A prime, A prime. So this can get outside because this is just a number. Or A can act on this, which we know is going to give me this. So double prime complex conjugate say this is 4, 5. So if I take the difference of these two equations, what will I have? This side is 0, this difference, two numbers. These two components. Oh, so there are two things here. So either this can be 0 or this can be 0. Let's see the case 1. If this is 0, this means which satisfies the first half, that this is purely real. And let's look at the case. If this is 0, but now these eigenvalues, they are different, they are not same. Can be anything but different. That means these two states are orthogonal. Because this is inner product or more layman terms, dot product. And if the dot product of two states or two vectors is 0, it means they are orthogonal. So here we have two states which are orthogonal to each other, which corresponds to different eigenvalues. These are different eigenvalues which are purely real, and their states are orthogonal. So hence we have proved this theorem that if the eigenvalues of a Hermitian operator A, they will always be real, and the corresponding eigengets to these eigenvalues are always going to be orthogonal.